It's really awesome to have Ankit Sultana from Uber. I think, Ankit, you've been at Uber for a little while now,
Yeah,
working on a number of the backend infrastructure. So we are super excited to see what you guys are doing with real-time analytics, and the floor is yours.
yeah. Thanks, Jignesh. Like, it's very nice to meet you finally, and it's very nice to like also present in this group. Like, of course, this group is like quite well known. I think I first heard about the CMU database group like almost 7 years back, and but yeah, it's finally good to be presenting this. So I'll start with like a quick introduction of myself. So I am Ankit. I've been at Uber for a very long time now, almost 7 years, and I've been in the data space the entire time. Changed team like multiple times. For the past 3 years, like I've been in the real-time analytics space, and specifically we use the technology called Apache Beano, which I'll talk about today in depth. And
Our microphone. Sorry, 1 second.
yeah,
Ankit, give us a second. We are just gonna do an A/B adjustment here.
yep, sounds good.
So
Okay, go for it. Yeah.
Yes, so yeah, it's good to be presenting this, and yeah, we'll talk about like our architecture. We'll talk about Pino in depth. We'll also talk about the contribution that we have made and how they fit into the broader picture of OLAP. But yeah, I think to waste no time, I'll get started. There's like a lot of slides we have to go through, but hopefully this should be helpful for people from all backgrounds. I'll start with like what exactly like real-time analytics means today. So back like at least in the last decade, people used to assume that OLAP queries usually just mean aggregation queries. But today, like OLAP systems or the so-called OLAP systems are capable of doing like a lot of things from vector search to real-time upsearch to ingestion from real-time and batch sources, hundreds to thousands of QPS, uh, tenant isolation, massively big data sets. Like you can have tables as big as like almost a petabyte in a lot of cases. And you have like complex types in there, you have JSON in there. So today, like real-time analytics essentially means that just I want low latency queries. And so yeah, today like real-time analytics essentially means that I want low latency queries and I don't want any constraints on scale. Like I might have millions of events per second I want to ingest in real time. And by real time, I mean like the freshness has to be like less than a minute or so. And I might want to run like thousands of QPS on it. And I still want like 100 milliseconds or 200 milliseconds kind of latencies. So the RTA space today, like it's pretty broad compared to where it started a while back. And that is one of the important things to realize is that this space is growing like crazy. And it's still like it was growing like crazy at least in the last few years. It is still growing incredibly well. And now we are reaching a stage where the RTA space is like kind of like venturing into the batch space in a way. So you'll see like ClickHouse and Pinol has started offering features about reading Iceberg directly. But we'll get to that probably towards the end of the talk. That's not really our focus for today. Our focus for today is about how we use RTA at Uber. And this is how our overall architecture looks like. So we have at the core the Apache Pinot database. That is the core database that serves pretty much everything. We support ingestion from real-time sources in form of Kafka. And Kafka, you can think of it as like a distributed queue, durable, and yeah, it's just like a producer-consumer kind of a pattern. And multiple people can produce messages to topics, and you can ingest that topic into Pinot, and then you can start querying it in real time. And we also support ingestion from batch sources. So Spark and other jobs can also push data to Pinot. Then we use like Apache Zookeeper for the distributed coordination because we didn't want to like implement this ourselves. So we rely on Zookeeper. We also use like a library built by LinkedIn called Apache Helix, which provides like cluster constructs over Zookeeper. Because Zookeeper by itself doesn't give you like those cluster semantics. It just gives you like distributed coordination primitives. But Helix will give you like proper cluster semantics. So you have resources there, you have participants there,
your spectators there and stuff like that. And on the right side of the orangish boxes there, so that is our the first two boxes there in neutrino and Celer query proxies. So those are our query proxies that are serving all queries that are going to Pinot today at Uber. And what these power is like user facing tools. They power like observability, logs, traces, and a bunch of other things. So we have like hundreds of use cases at this point, thousands of tables, and scale is just like pretty large. And you can think of like real-time ingestion as visually in this form. So you can think that there's like a stream of messages coming through a pipe, and you can ingest them to a table which follows your standard relational model. And every message in the pipe essentially becomes a row in the table. And you just keep on appending rows this way. So as messages come in, you keep on appending rows. And one of the key things that Pinot did was that, and this was something that Droid also introduced, which is that we use Kafka as a write-ahead log. So, for example, like to contrast it with this with ClickHouse, like ClickHouse like allows you to like push data to ClickHouse, and ClickHouse takes care of all the write-ahead log management as well as the distributed coordination across servers about making sure that the data is replicated. In Pinot's case, like the only thing we have to do for replication and anything else is just make sure that we have Kafka consumers across our servers. So for example, if let's say you set the replication of your table as 3, then for each Kafka topic partition, you will have 3 consumers across different servers consuming from the same Kafka topic. So the problem reduces quite a bit for us because the only thing because Kafka takes care of all the heavy lifting around making sure the individual messages are durable and repeatable. We only have to track like offsets. So we just care about, okay, I am currently reading at this Kafka offset, let's say 100. I'll read till 200, then I'll commit a segment, then I'll continue from 201 to 300 and so on and so forth. So that is like one key concept in terms of like the ingestion side of things. But anyways, like today's focus is not on ingestion, it's on the query side of things. So we'll start diving into that. Pinot's architecture overall it looks like this. So we have Pinot controllers, which are the brains of the cluster. And we don't need to like talk much about them, but you can just think of it as the central unit which manages everything. Like you create tables against the controller takes care of tracking new servers coming in, tracking new brokers coming in, and stuff like that. And Pinot by default has this tenancy concept. So you can create like isolated tenants for brokers, isolated tenants for servers, isolated tenants for minions, which are used for like ad hoc jobs. And that gives you like isolation across your use cases. And this is like a pretty important feature, especially for like modern OLAP systems. Like if you don't have tenancy, then it just makes it very hard for you to like build a platform around it because as a platform you would be serving like hundreds of use cases across like maybe like 50 or 100 plus teams, and you don't want like all of them to be able to affect each other, so you want isolation from the beginning, and Pinot does provide that. And the query execution model is that you send a query to Pinot brokers. Pinot brokers are stateless. They take in the query, they'll compile it, plan it, and send it out to the servers. Servers are the ones which have the data, so they are stateful. And they might shuffle data in between them, and ultimately they'll return the data to broker, which finally reduces the data and then returns it back to the client. So that's pretty much the high level Pinot architecture. And I'll pivot here to the internal stuff at Uber, which is the first thing I'll talk about is Neutrino, which is our still, I think, serving most of our Pinot traffic at Uber. And this is the query proxy. So query proxy's role is to integrate the core database with the rest of our ecosystem and essentially become like a central point where people and customers send their queries.
So, Ankit, just to ground the rest of the talk, can you give examples of services that run in Neutrino?
Yes. So Neutrino itself is like a microservice. And the kinds of use cases that we have are so we support logs. So all the logs at Uber, those are stored in Pinot. And the front end where you browse the logs, like those end up like sending queries to Neutrino as like SQL queries. And that is one use case. Then we also have like a lot of observability use cases. So think of it as I can give you like one example. So let's say in Delhi, in India, there are rides happening, and we have these events of trips coming in. And I want to detect that whether there's like any anomalous event happening in the last 30 minutes or so. So I can write like pretty complicated queries against Pinot, because the advantage of Pinot is that you can have like these wide columns that we showed before. So you can have like a bunch of columns in here, and then at query time you can choose to combine these columns howsoever you want. For example, if let's say in this particular case, like I want to set up an alert for tenant 1, and I want to set it up in a way that if let's say the total documents count over a given period of time exceeds a certain value, then I want to be alerted about it. So it's like a single table can power like any sort of a analytical query. So that is where like alerting wise like Pinot is very good, and it can handle like high cardinality alerts well. So high cardinality alerts essentially means that you can store UUIDs in Pinot, and you can still use it as a time series engine of sorts, which is something that a lot of time series engines struggle with, at least the ones that are publicly available, and even like a lot of SaaS companies.
Got it. Thank you. Appreciate that.
And I think one another use case I'll probably call out is we also power like a lot of end user facing apps. So I think you might have seen those tablets being run in restaurants, which have the Uber Eats application running in them. And we have like a lot of analytical features powered through Pinot there. So for example, like how your order cancellations are doing over the let's say last 7 days or so. So all of those graphs and analytics, those are also powered by Pinot. And that is just like the tip of the iceberg. Like we have too many use cases at this point to even call out. But yeah, so starting with Neutrino. So Neutrino is like a state. I'll also like talk about the architecture in the next slide. But it's like a stateless microservice, and it is a proxy. But the way it is unique from other proxies is that it is also a query engine. And the how this happened was that it is essentially a fork of a technology called Presto. So you folks might have heard about Trino. I think Trino is more popular these days, but both of these were kind of the same thing a few years back, until they diverged and forked. But we have like this internal Presto fork, and it is a modification on Presto. So Presto is like a distributed query execution engine. So Presto doesn't give you the data itself. So your data would be stored in some database or some file format in GCS, S3, or what have you. And but what Presto gives you is like a SQL layer on top of it. So you can run like queries against your data lying anywhere you can think of. And you can run like join queries, you can run like very complicated subqueries and stuff like that. And the way it works is that it is like a distributed query execution engine. And Presto has like a lot of workers, so you'll probably spawn like hundreds of workers across a bunch of servers. And it has like 3 or 4 coordinators that you use for becoming the brains of the cluster. And the workers do all the processing, and the coordinator becomes like a central nervous point where the coordinator is where all the clients also interact. So they'll send queries to the coordinator, for example. But what we did was that this model is good, and Presto has been like a very big success at Uber. Like it is a very reliable system, but it is designed for like tens of QPS, and it is designed for latencies which can go anywhere from like 10 seconds to up to like 30 minutes. So it's not really designed for the low latency real-time analytics systems that we want. So we created like a fork of Presto, and we made some changes in it to combine essentially the worker and the coordinator into a single process. So instead of now deploying our Presto fork as a cluster, we now just deploy it as a single process, and that process is of course like replicated in a standard microservice architecture. And what that gives us is that because it's single process, the latencies go down significantly, and you can serve like a very high QPS on top of it. And just to give like some examples of latencies, so right now today we support anywhere from like 10 milliseconds to up to like 15 seconds or so. The latencies can really vary. That is another thing about OLAP systems, that it's not necessary that your OLAP system or distributed OLAP system is only going to serve like 1 second or 10 millisecond of latency of queries. It can also serve like 15 seconds to up to like 2 minutes in some of our cases. So the kind of workload that we support in the platform is like pretty diverse. So that also introduces a challenge that we'll talk about probably in a future slide. But this is how the architecture looks like. So you have these neutrino containers running in a stateless ecosystem. Think of it just like uh, just processes running, and these are discoverable through like a standardized way. So the clients don't have to know about where the process is running, but the process might be running across like hundreds of containers, which might be spread across like 50 or 100 plus servers. So yeah, users send us Presto SQL because Neutrino is a fork of Presto. So we still accept and only accept Presto SQL from customers. But it does like a bunch of stuff. It figures out like where which Pinot cluster I have to send this query to, and then it sends a Pinot SQL to Pinot because Pinot doesn't understand Presto SQL. So that is the key thing to note here is that we are doing like SQL to SQL translation in a way, and that is probably going to be my main focus point of the Neutrino architecture is that that is not a great or tenable idea when you're running things at scale, and I'll get to like why that is the case. But to talk about like how Presto SQL to Pinot SQL translation happens, I can like, and all of these are like also like, all of these pictures, like these are also coming from our recent engineering blog, which I've linked towards the end of the slides. I'll send out the links to you separately as well if required. But uh, yeah, so the query pushdown functionality, it works this way. So users send us complicated Presto SQL. Like, so for example, on the left, we have a query which has a subquery, which is doing a group by first. Then I am running a window function on it. And then I'm running a filter with an aggregation. And the whole thing that it is doing is it is essentially like in our data store, we might have duplicated events. So what it is doing is it is like deduplicating them based on the latest timestamp or the latest version of every record. So this is like a way to implement like runtime deduplication. And users are sending us this Presto SQL, but the challenge for us is that Pinot does not, at least Pinot couldn't handle in the past queries like this before. Pinot could only handle queries which have a single select clause, single from clause, single where clause, single group by clause, and single limit clause. So it could only handle like what I call these like flat queries, but it could only handle these flat queries. It couldn't handle like subqueries or window functions or what have you. So the way this works is that we create a plan out of the Presto SQL that users send us using Presto's optimizer. And Presto will run like a bunch of optimization. It will create like a final plan. And we take that final plan and we run like our own specific optimizer on top of it. And the what our optimizer does is like it only works for like a chain of a plan node. So your plan tree can only be a chain. It cannot have forks. So it cannot be like a join in there. But as long as your plan is like a chain of nodes, we'll figure out the maximal subplan that we can push down to Pinot, and we'll convert that thing to a SQL or Pinot SQL. And the rest of the plan nodes will be run within Neutrino, and all of them will get compiled to the corresponding operator implementations. So for example, in this case, like I am able to push down the first subquery. So the select from where group by 1, 2, 3, 4, that part I can push down to Pinot. But the rest of the part, because Pinot doesn't support window functions. So from there on, everything else is run within Neutrino. And that is where like this unique architecture kind of comes in. But I'll pause for like questions.
Ankit, quick question on that. Do you have to worry about semantic differences in type handling or functions when you have more complex functions between Presto SQL and Pinot SQL, or you don't run into rounding errors or other types of type-related uncompatible ways of doing the same thing? You get a different answer depending on whether you ask Presto or Pinot.
Yes, that is exactly the issue with this. I'll just touch on it in a, I think probably in the next slide or the slide after that. But that is exactly the issue that layering SQL over SQL, it is good if let's say you are doing it for just ad hoc kind of use cases. But building a platform on top of this becomes a very big challenge. And But before I get into that, I'll talk about the pros of this architecture. So the pros are that, like I talked about, like Pinot only supports these flat queries, and Presto supports like arbitrarily complex queries. But we don't allow like joins or anything that will create a fork in the plan. But as long as you are dealing with subqueries or multiple aggregations or window functions, you are pretty much good to go. So people can write like all sorts of complicated queries and still be able to get results out of them. With Pinot alone, this wouldn't have been possible. So that is one immediate advantage of this. And we have actually seen this be a very big success at Uber because I think almost 40% of our queries today are leveraging this feature of Neutrino, that you can write any complicated query, and even though Pinot doesn't did not support it before, you can still get results out of it, even though there are caveats around it. Another thing advantage here is that if you look at the SQL, like when we are sending a SQL out to Pinot, we would inevitably have to add a limit here. Because if I don't add a limit, then Pinot will default to like a limit of 10 or whatever default limit is set. And we don't want to allow people to like send arbitrary limit queries to Pinot. So for example, if let's say someone was doing like a select star from table limit 1 billion, and that table has like very wide rows, then that would trigger like very big scans, and that could just impact the cluster and degrade all the other queries that are running on that cluster as well. So we have to put like a sensible limit on the maximum number of rows you are allowed to return, and that is achieved by adding a limit in the generated Pinot SQL query. So that is another kind of good thing about Neutrino, that for every query that is coming in, we are able to ensure that the resources would be limited by adding a limit ourselves. Or if let's say a user has added their limit, we'll just take their limit and add it to the query. So that is also good. So that makes the system like hard to break because people are not able to like run arbitrarily complex queries, and the cost of every query is like kind of like capped. And finally, like there are like general advantages of like having a proxy, which I won't get into. Like these are like very generic, but the cons are also pretty big. So like I think Jignesh also hinted at, when you have SQL over SQL, it almost becomes impossible to map certain semantics because every database has their own quirks. I know that a lot of people are trying to be like Postgres SQL compliant these days, but to be fully like but at the end of the day, like most databases still don't have like a single semantic. Like even though like a lot of SaaS vendors are selling Postgres SQL compliance, most of the databases still out there have their own semantics. Like Trino, for example, has their own semantics. Presto has their own semantics and own features, and the features will never be one-to-one compatible. So layering one SQL over the other, especially when your other SQL is actually a distributed SQL. So Pinot is like a distributed system, unlike Postgres or MySQL. It's not a single node system. And that also introduces like a bunch of complexity, which I'll talk about, and which makes it like even further harder to map certain semantics. So yeah, is one challenge, and what that inevitably means is that we have like very hidden push down semantics. So people, if their query is working fine today, they might add let's say one UDF tomorrow, and that will just break query push down, and suddenly their generated Pinot SQL query will change very drastically, and they might not obviously expect that this to happen, but how to surface this issue to people is a very big challenge. Like we had a very hard time figuring out like how to notify people of such things happening, and ultimately we realized there's no good way to do this because fundamentally the system is just not designed in a way to be used the way we were using it, which is we have like hundreds of users, everyone is just onboarding new use cases every day. People are also running like Haddock queries on top of Neutrino. So it wasn't just designed for what we ended up using it for. And another disadvantage here is that there's like a very hard dependency on Neutrino. So my clients cannot directly query Pinot because the proxy takes in only Presto SQL, and because it has its own query execution engine, if I ask people to okay, you can also query Pinot, then they would have to use a different query language. So that is like another learning curve, another integration pain point that I have to deal with. And because everything goes through Pinot, everything goes through Neutrino, we end up breaking tenant isolation in a lot of ways because we cannot create neutrino environments for every Pinot tenant out there because of like architectural reasons. So we are stuck in a design where one neutrino environment will be serving like 20 different tenants. And that essentially like breaks tenant isolation, which is something we really, really wanted from the system. And it also cannot support like Pinot's latest feature, which I'll talk about in a future slide. But yeah, all sorts of cons there. That is where we decided that we have to support Pinot natively to our customers. By natively, I mean that users should be able to write queries as Pinot expects them, and we don't want to introduce like any translation layer or any query execution on top of Pinot. And what we instead want to do is we want to support all the functionalities within Pinot itself. So if whatever like Neutrino plus Pinot system was able to do in the pros section, we should be able to do it natively in Pinot. And that was the vision we started executing on like almost like 2 years back. And we slowly worked on it. And today we are at a point where we have almost like achieved it. And yeah, so this the new proxy we are calling it seller. The proxy like is like it's literally just a proxy. Like it does some validations around like syntax checking and stuff, but it is very simple. It's very lightweight. It's almost like 10x more efficient than Neutrino. And this is the overall architecture. It's pretty similar to how Neutrino was, but one difference that we went with this time was that we also like supported clients in Java and Go for people, because most of our customers are have their applications written or backend services written in Java and Go. So we this time we supported our officially maintained clients for the seller service for both Java and Go. And what that means is that for a new user to onboard, it's very seamless for them to like get started with the system. Another thing is that the response returned by Pinot and most of the other databases these days is pretty complicated. Like for an average user, like they wouldn't have time to go through all the JSON spec and figure out, okay, this means partial results, this means this particular error and stuff like that. And we've seen that with Neutrino also, like a lot of times people will make Neutrino HTTP calls and they'll just rely on the HTTP status code for errors. But Neutrino can also return errors with HTTP 200 and the error in the one of the JSON fields. So we had a learning from that experience. So we are giving our own clients have very neat interfaces around when an error will be thrown, when partial results are returned, and it also has like a bunch of other bells and whistles which I'll talk about. But one quick thing to note here is the 4.1 and 4.2, which is that we not only accept SQL now, we also accept M3QL, which is a time series query language we use at Uber. I'll talk more about it in one of the slides that is coming. But TLDR of the seller architecture is we take in whatever users send us and we pass it on to Pinot without any modifications.
Does Pinot natively support M3QL?
Sorry?
Does Pinot natively support M3QL?
Yeah, the way we did it was through a generic time series engine. So Pinot can support almost any time series query language, including PromQL or Uber's M3QL and so on and so forth. It's configured through like a plugin architecture, and the plugin allows you to like even plug in your operators and plan nodes and stuff like that.
And then what was the hard part? So you said it took 2 years to build proxies. You're not doing, other than you're just doing query validation, or maybe permissions lookup to the metadata service. Like what took 2 years to build this?
Yes, so Pinot itself did not have the full SQL support that Presto had. So we had to add that in Pinot, and that is something we started executing on. And outside of just the proxy itself, there were like a lot of architectural components we had to do. And I think one thing I'll call out is that it wasn't like we had like 3, 4 engineers just working on this the entire time. One of the ways our team operates is that we work in a way that we can work on long-term vision, but we have to like show impact every 6 months or so. So we also like multiplex with like a bunch of other projects. So throughout those 2 years, like I had like engineers coming in, coming out based on their availability, and we kept on executing.
Okay, but I think you also just said too, you expanded the SQL syntax that Pinot actually natively supported to do more custom things, right?
Sorry,
Yeah.
okay. Can you repeat that?
That like you say that you had to expand Pinot's SQL support to now support more custom like things, right?
Yes.
So like
Okay, and that made it upstream to Pinot?
Yes, that is all of those features are open source today.
Okay, and then so then what things that Presto can do that you guys currently can't do? Can you do like CTEs and subqueries or no?
Yes, we can do subqueries, we can do window functions, and we can do shuffles as well. So
Okay.
all of those things are doable. Some things we don't do as well as Presto. So Presto can spell data to disk when someone is trying to like run a very expensive query. So we don't have data spelling to disk yet. We are completely in memory still. And another thing is like I think I would still say like Presto is very good at handling like a very diverse set of workloads. So you can write like an arbitrarily complex query, and Presto can make sure that other queries won't be impacted and just your query will slow down for a certain point of time.
Right. I said, what at this point, what percentage of the users at Uber are going through Neutrino versus Seller?
In terms of users, I think we are number of users is only like maybe 10 to 20% because Neutrino has a very long tail of total number of customers. But QPS I think is already around 40% or so.
Okay. All right, thanks.
Yeah, and it also like we also serve like very critical architecture already, use cases already. So we essentially did it in a way that we prioritize like the bigger use cases first, and we'll go over the long tail over time, probably next year. But and actually, I'll talk about the multi-stage engine in depth in the upcoming slides. But before I just wrap up the seller section, right? So the pros are that semantics are simple. I'm not introducing like, query execution engine on top of query execution engine. Like whatever Pinot defines are my semantics. Apart from like some very basic validations, for example, for limit, I will still need to add certain validation. Like I cannot still allow people to write like select star limit 1 trillion or something, right? Uh, so there's some validations there, but those are very simple, just literally just like one line kind of a semantic. Then you have access to like Pinot's full feature set. So you have access to the multi-stage engine in Pinot, which I'll talk about. It's a new engine, I would say like a relatively new engine. It's like almost like a year and a half old now. And we also support access to the time series engine, which powers the M3QL, PromQL use cases that we have. And there are like some other like implementation kind of stuff I won't get into, but one of the important things is that we also support a way for you to like bypass the proxy, and that will give you like true end-to-end tenant isolation. The way that works is that seller client will just reach out to seller for the coordinates of where Pinot is, and from there on it will just start hitting Pinot directly. So that way, what often happens with OLAP and real-time analytics use cases is that we will have one use case which wants 5,000 QPS, but all of our other use cases combined will have less than, let's say, 2,000 QPS in some environment. So we don't want that lopsided traffic to be co-located in the same environment. And what this allows us to do is like just have them bypass the proxy altogether and just have them hit Pinot directly. So that way they just get like true tenant isolation and a bunch of other bells and whistles that come from it. But yeah, so we gave full access to Pinot, and that was our vision. But did not support. Pinot only supported like flat queries. It did not support like Neutrino's full feature set. And the thing about that is that we are doing this in a distributed setting. So it's one thing to like support full SQL on a single node kind of an installation, right? Doing it in a multi-node system introduces like a bunch of challenges, which I'll talk about shortly. But right today, like Pinot has two SQL engines. One is the single stage engine, which is the one that originally existed and supported those so-called flat queries. The multi-stage engine supports like full SQL. It can do shuffles across the servers, and it can basically you can pretty much write anything that you want. Either Pinot will like run out of memory, or we will be able to compute it well. I'll dive into it soon. The single stage engine has a scatter gather architecture. It supports a smaller SQL feature set, but it has the advantage that your query execution is kind of bounded by default because it's very hard to write a single stage engine query which will break the system. The multi-stage engine, on the other hand, like it can do shuffles, broadcast joins, what have you. It does full SQL, but the query execution is kind of unbounded. So if, for example, we have some tables which have almost a trillion records, and you can, because semantically, if you write a query, we have to honor those semantics. So you can technically trigger a full scan of those 1 trillion record, which will just take forever and we'll have to probably uh, intervene to mitigate that situation. So this is the single stage execution model, scatter gather. It's a age old design. It works very, very well. And this is one of the reasons we ended up borrowing the scatter gather design for some other feature I'll talk about pretty soon. These are the flat query query structure that is usually there. You have single clause of each type, where group by, order by, limit are like kind of your optional clauses. We already talked about these. The multi-stage engine, like the execution model there is like shuffle based. So broker will dispatch like query fragments to servers, and servers will send data between each other as they need to, and run all the operators, and finally return the computed result back to the broker. So that is how like the multi-stage engine is and was, and it supports like full SQL, like you can do cross table joins and what have you. But it introduces some challenges which need like some immediate thought. And for context, like I'll also share, we were like one of the first teams across I think all companies to adopt multi-stage engine for a production use case. This was like almost 2 years back, and at that time multi-stage engine was in a pretty nascent state, so it was still unstable, but we somehow managed to like onboard it for one of our use cases. And back then we realized that, and that use case relied on partition data, and that is where we started working on certain optimization that I'll talk about. And before I get into that, I'll talk about shuffles and why they are bad. I think you folks might have already uh, learned this as part of your course, but let's assume that I have a join plan node. This is like, let's say, a logical plan tree. And I'm doing a join. I have scans on both sides. Maybe they're very small tables. I don't worry about full scans. And let's say I have 4 servers. So the way this usually runs in a distributed setting is, and for the sake of argument, let's assume that we have the tables present across all of these 4 servers. So your scan 1 will run across all those 4 servers. Your scan 2 will run across all those 4 servers. And your join can run across any number of nodes, because that one doesn't really care about uh, which servers it is assigned to, as long as the scans can send it data in the right fashion. But let's say that join also runs across all those 4 servers. So this is how the physical manifestation of this plan would look like. Your scan1 will run on all 4 servers, scan2 will run on all 4 servers. For now, we'll run join on all 4 servers. But this leads to this, which is a shuffle. And as you can see pretty clearly, like this introduces like a bunch of things which we'll talk about. But that is something we don't want for a lot of reasons. And what we ideally want is, if let's say I have to do this data transfer, I would ideally like it to be this. So this is much better intuitively than this. And the reason for that is like shuffles do enable correctness and completeness for queries. So shuffles are, and by the way, like shuffles are also represented as exchanges in the plan node. So shuffle is like a part as a kind of exchange. Although don't take me on my word for terminologies, because I'm an engineer and we just make up terminologies on the fly. But uh, shuffle is like a part, is a kind of exchange, and it allows you to like compute correct results, and it allows you to like provide completeness for your queries. But it introduces like a bunch of performance issues. The first one is obvious, n cross n, and that essentially breaks horizontal scalability. The idea of horizontal scalability is, I'll just keep on adding more servers, and I'll expect the performance to go up at least linearly. Is like hard to achieve even in most systems, but roughly linearly, or just sublinearly. But linear is actually also possible. I don't need to get into details there, but that is the overall idea, that you add more servers and you get more scalability. But if you are doing shuffles, then your n cross n factor starts becoming a bigger and bigger overhead as you just keep on adding more and more servers. And that is something we saw for our use case 2 years back, because we had like a lot of servers for that use case. That was a very big use case. And we just couldn't afford to have this bigger cost in our system. Then there's like also the SerDes costs that come from just the data transfer across the wire. There's the context switching that comes, because as those shuffles are running, so essentially let's say I am a server, I'm part of this 4 server group. for my join computation, I'll expect to receive data from all four servers on both sides. And that just adds like a lot of context switching, because let's say my left side of the join will send me data first, then the right side will send me data, then the left will send me data. And if I'm doing like a hash join kind of a thing, one of the strategies to run a hash join is to stream all the results from the right side of the join and then start polling the left side of the join. So it adds like all those scheduling complexities and context switching costs, which end up becoming like a very big cost overall. It makes debugging very hard, and it also like introduces like inter-server dependency, which we don't want in a system. Like you don't want users to be running queries, and that just creates like one server is slow, and now all servers are slow because all servers have to wait for that server to send it data, and they also have to maintain a lot of data in memory while queries are coming in real time by the user. So all of those issues are there. Then there's also this. This is a slightly niche optimization, but it starts coming up very early on in your multi-stage kind of queries, and I'll talk about like some other systems as well soon. But the problem here is that let's say I'm running a count star group by user ID on a table scan. If my table is distributed across the servers, to compute this accurately, I would have to make sure that I have the user ID, the data distributed by the user IDs, because I just cannot compute this locally on every server unless the data is partitioned on user ID. But even then, I would have still have to add like one additional aggregation step on top of this. So what people usually end up doing is like you have your aggregation on top of your scan, and we'll add like a shuffle or an exchange in between there, and that just solves the problem. So after your scan, you can distribute data on user IDs, and then your aggregation can compute results correctly, but it would be in different streams. But that is fine in a lot of cases. Like at least for SQL, distributed SQL, that is fine. Uh, but yeah, it will at least like it will start producing data correctly, even though it's in a distributed stream kind of a setting. And by distributed stream, I mean that let's assume that we have one stream of operators per server. Then after the aggregation is done, I will have four streams which have the aggregation results, and all those four streams will have a subset of the user ID aggregations in them. And I can use them to compute the rest of the query operators unless like I need another shuffle, in which case I'll have to reshuffle data again and do something else. So yeah, aggregation splits. So this is one way to do it, but this is very costly because what this is doing is I am passing the entire data across the wire. So what people usually end up doing is they insert a aggregation underneath the shuffle, and this is what we call like an aggregation split optimization. And what this will do is like just after your scan is done, you immediately aggregate data. And if your data is like if you're like a tightly coupled system like Pino, then I can just even avoid like doing the scan. I can directly execute aggregations using just the indexes I need to read. So this is good and all, but what I initially wanted was this, but what I've ended up with is one shuffle and one additional aggregation. And this becomes a pain when you have like a lot of your group by column is very high cardinality. In that case, this will be very costly because group by at high scale tend to be a very big cost in most of the queries. For context here, like Data Fusion they I think shared a blog last year where they talked about how they dynamically take a decision about whether they want to split the aggregate or not at runtime. But what I wanted to share is that every database system is always thinking about this particular optimization alongside the shuffles that we talked about. And that is where we built the physical optimizer in the multi-stage engine. This is something we productionized early this year. And what this can do is like it can simplify shuffles automatically uh, to something what I call identity exchanges. So identity exchanges mean that there's like a one-to-one data transfer across stages of the query. And it can also like auto simplify those aggregation splits. So for example, you'll see that this, I'm not sure if you can see the cursor, but in the query plan, there's like a direct arc type equal to direct highlighted towards the bottom. And here what I'm doing is like I'm merging the aggregation with the leaf stage of the query, and Pinot can execute that very optimally. So instead of doing like two aggregations and a shuffle, now I am just doing a single aggregation. That goes a long way. And it's probably a tangent, so I won't get into it. But essentially, for a query on the right, so the query on the right is actually like a sample query that we run in production. Of course, the table names and everything is changed. But the tables involved here is user attributes, user groups, and user fact events. And all of these tables are partitioned on user UID. But and the plan for this query is the one shown on the left. And this can run on like any number of servers, like 4 servers, 8 servers, 32 servers, what have you. And we'll still be able to simplify shuffles to one-to-one exchanges. And we'll still be able to simplify aggregates and eliminate like aggregation splits. So that is something we did earlier this year. And these two optimizations alone, they yielded like 5 to 7x faster queries. Actually, for some of the queries, it's almost like 10x faster, while consuming half the CPU that we consumed if we were shuffling and also doing those aggregation spreads all the time. And just for context, with this uh, use case scans like billions of records, almost a billions of records per query, and we the user UID column is very high cardinality. So that is basically completely nearly unique. So that is another reason why the optimization that we talked about really help, because your group by cost continue to increase as your cardinality increases. For lower cardinality use cases, splitting the aggregate should be okay. But for higher cardinality, you definitely don't want to do it. Yeah, I'm also like rushing because we have to make time. But yeah, the second kind of problems that we solved with MSC was unbounded execution. So people can run any kind of query. That means that people can break the system very easily. And doing supporting this in an OLAP system where people expect latencies for their production use cases to be 10 to 100 milliseconds for the most part. So if they're expecting that and we also allow them to like run anything that they want, then that is just a recipe for disaster. It's not about like how your query scheduler is designed or how your runtime is designed. You pretty much cannot do anything about it because people can write any sorts of queries, and you would be surprised to see like the kinds of queries people write. But people can write any sorts of queries, and if the system breaks, it would be on you as a platform because you were supposed to make sure that you provided the right contract to people. Like you cannot open a system to people that they can easily break. So MSC introduces that particular unbounded execution problem, and we recently solved it with something we're calling the light mode. It is pretty similar to how ClickHouse also does joins, because ClickHouse doesn't do shuffles. My understanding is that they also do like a scatter gather based join, or they do like a completely local join. But yeah, the MSC Lite mode, what it does is like it takes the learnings from Neutrino and it brings it to Pinot. And this is the feature that essentially helped us complete that feature parity gap between Neutrino and Pinot. And the way it works is that we still do scatter gather similar to the single stage engine, and we have completely eliminated shuffle. So there's no way you can trigger a shuffle with this. And the reason this works is that after your first stage is run, we send all the data back to the broker. And to make sure that the broker cannot run out of resources and the users cannot write very expensive queries, we have limits on the amount of data that users can send from the leaf stage. And this can support like high QPS, low latency queries at the trade-off that your data is limited that is sent from the servers. And this is an important design choice because what we are saying is that we cannot solve that MSC full problem in the OLAP space. We are not Presto. Presto can solve it because it can afford to give higher latencies occasionally. We cannot do it because we have to strictly be 50 milliseconds, 100 milliseconds for like almost 90% of our use cases. So this is our way to like essentially give people like full SQL support, give them clean semantics. So for example, in this case, like if someone hits the data limit set at the server level, we'll notify them with a warning that something happened and you need to do something about it. So this is essentially something we recently productionized and we're still rolling it out internally, and it's available in the latest Pinot version in open source. This basically goes to the same thing I talked about. We have 4 minutes. I'll just go over the time series engine stuff, which is also pretty cool. So the time series discussion started coming when a lot of people at Uber are using Pinot for observability use cases and Grafana for alerting and stuff like that. And they were having a very hard time just navigating around SQL. So they were just trying to build like all sorts of hacks to just make their use case work. And what we thought was, okay, can we support M3QL, which is our native Uber time series query language, on top of Pinot? And initially, there was a project started to just translate M3QL to SQL, but we quickly realized that that is just not going to work out. The data modeling and the way you think about data in the time series model is very different from how you think about it in the relational model. So we decided that okay, like can we add this very cheaply in Pinot? Like can we natively run M3QL operators in Pinot? And we figured out a way to do it. I won't go into the details of how we did it, but I'll show one example. So let's say I have this query. This is an actual M3QL query with like a dummy data set. By default, you would have like gaps in your data. One of the common things that you want to do is gap fill. And gap filling in SQL, people have built like all sorts of ways to just achieve it, but it tends to be very hacky in almost all of those cases. And the default SQL way, or by default, I mean, if let's say you were to use non-gap fill specific functions to achieve this, it is like a very complicated query. Actually, one of our users ended up writing that query. It uses like a bunch of Lambda functions, generators, and what have you. And even I was surprised because I couldn't think of writing a query like that, even with like all of that experience in Neutrino. But anyways, so gap filling in M3QL is just like a literally single word. You add a single word, now you have gap fill data. Uh, then another requirement is like you have to smooth data. So in this case, like my data is very spiky. I just cannot derive any insights from this or set up any alerts on this. So smoothing is usually done using like moving functions or something like that. And again, like it's just a single word. Moving functions are not that hard in SQL, but uh, combined with gap filling, they are still hard because you still have to do gap filling to do moving functions. Otherwise, there are like some caveats around it. I would say like it's a good exercise to like think about like how you can do these time series functions with SQL. And yeah, finally, you can also like write queries like this. These are all run natively in Pinot. And the way we achieve it is through a very layered query engine architecture. So we have at the core of Pinot the leaf stage engine, which abstracts out the column data, index reader, all of that logic. It abstracts out how ingestion is being done, everything else. And it has a very simple API. The input is a server plan request, which takes in group by expression, select expressions, and stuff like that. And the output will be a block. And using this primitive, now we are supporting like three engines. We have single stage engine, multi stage engine, those are SQL engines, and then the time series engine. All of them have their like own planner and runtimes, but they're also like the components are pretty much shared, so it's not like a lot of code being added on top of it. But that is like one good idea that Pino I think did really really well. This is the conclusion. I think we've gone over this. So I won't dwell on it. And yeah, finally, there's like a bunch of links towards the end. I'll pause here for questions, but I think we are just out of time.
That sounds great. First, let's give you a round of applause. Okay, questions?
I mean, you basically want a system that has the SQL semantics of Presto, but the timeliness of Pinot, and then the time series capabilities of M3DB. Is that correct?
Yes, and I think this also goes to the fact that we started with one problem statement. OLAP was real-time ingestions, flat queries, SQL queries, very limited features. But now we are pretty much getting to do whatever that's out there. So vector search, for example, is also there on Pinot. And even text search is also there. We use it for some of our big use cases too.
Sure. Yeah. Okay.
And from the backend infrastructure perspective, do you have a philosophy in terms of whether you're going to run all of this stuff on small number of large containers or large number of small containers or something else? Like what do you do with the allocation of the resources in the backend?
Yes, I think I probably cannot dive too much into it, but I would say that is one of the unexplored areas right now. I think that is probably going to be our focus in the next 1 to 2 years. I think so far what we were very focused on was because we were get this platform took off like crazy. People like had like all sorts of use cases, and to support them, we had to add all of these features. So it was like very features focused the last 3 4 years. I think the next few years it will be more focused around, okay, can how can we just get the maximum out of whatever we have. Although like Pinot is already quite optimized, so I can tell you this much that there was a month where I thought, okay, Pinot has a lot of low hanging fruits, and I'll go in and optimize certain things, and I figured out that's way harder than I thought. Like it's at least like it's optimized to a point that the next optimizations are only going to yield like 20 30% kind of improvements, and they will be like a lot of work. So we are pretty much maxed out there, but I do agree that on the allocation side of things, there is like room for improvement still.